All right, let's do a couple of examples. So let me just read the instructions first. It says, we will consider friction in each of these problems. These problems are the first two from our first energy problem set. I have not passed this out, but you can find these problems on OneNote Problems, Energy PS number 1, Energy Bar Charts. So I'm going to do the first two. The problem set has 8 problems total. So tomorrow you'll have a chance to work on the rest of the problem set. So we have in problem 1, a ball is held above the ground and is dropped so it falls straight down. At the final position, the ball is still moving in the air and is at the point right before it hits the ground. And you'll notice we have 3 points for the ball, and we have 3 bar charts. You'll also notice that there are arrows beside the ball, and those indicate something about the ball's velocity. For the first point, we have no arrow, so the ball is at rest. Then we have a short arrow and then a longer arrow showing that it's getting faster. So for the first bar chart, the ball clearly has a bunch of gravitational potential energy because it's in the air. It has no kinetic energy because it has not stopped moving. There's nothing elastic in this problem, and friction has not yet had a chance to act and create heat. Now, I should say that not only does friction create heat, but so does air resistance. So this is the bar chart for the very first moment in time. Now, in the second frame, the ball has fallen, so it's not quite as high up in the air, so it has less GPE than it did before. The ball has started to move, so it has some kinetic energy. Now, at this point, we don't know, does it have more kinetic energy or more GPE? That's not something we've focused on yet, so it's okay at this point if you don't know which is taller, KE or GPE. We just know it has some KE. We also know that it has traveled through the air and it has encountered some air resistance, which has generated some heat. So we have a small amount of heat that has been generated. Now, ideally, if I stack these bars up, like if I take this kinetic energy bar and I put it on top of the GPE bar and I put the heat bar on top of that, they should all be equal in height to this initial GPE bar because we know that energy can neither be created nor destroyed. It is just transformed from one form to another. All right, in this final frame, we've got the ball is right before it hits the ground, so it essentially has 0 GPE, and it has turned basically into, all the energy has turned into KE, or rather most of it has turned into KE. Again, there's nothing elastic, but air resistance has created more heat. So we're going to have a heat bar that is a little bit bigger than it was before because air resistance has now generated heat along this entire path. Again, if I stack this heat bar on top of this KE bar, it should equal in height, equal the height of this GPE bar. I don't think I have it exactly right, but I'm trying to be close. All right, let's do another example. This example is a little tricky. We have a wind-up toy. A wind-up toy is wound up, then walks across a table and comes to a stop. Inside of a wind-up toy is a spring. It's a coiled spring that looks like this. As you wind it up, the coil gets tighter and tighter. And then when you release it, the coil springs out and makes the wind-up toy go using gears and other sorts of mechanisms. Now, as you'll notice, this wind-up toy, according to this arrow, is already moving by the time the problem has started. So a lot of times we think of wind-up toys, they start initially from rest, but we're not starting from rest. We're starting from the point where the wind-up toy is already moving. And you can see that this arrow is getting shorter and shorter until it stops. I think for this problem, what I'm going to do is I'm going to go one energy at a time. So first I'm going to focus on KE, then GPE, then EPE, and then heat. So initially, this wind-up toy has a bunch of KE. In the second frame, it has less KE. And at the end, it has no KE. In terms of GPE, This toy never leaves the ground, so it doesn't have GPE at all in any of these frames. Now, elastic potential energy. The toy starts off with a lot of elastic potential energy, and as time goes on, it uses up that elastic potential energy, and it has less and less and less until finally the spring is uncoiled. I don't know initially if it has more EPE or more KE, so it doesn't really matter. I'm just going to take a guess. I'm just going to say, let's suppose it has a lot of EPE. But over time, it's going to have less and less. So less EPE. And then finally at the end, it stopped. So presumably it has 0 EPE left. All right, now you'll notice that we have loads of energy in the first frame, a medium amount in the second, and not very much at the end. So something must have happened to that energy. Where did it all go? Well, it must have turned into friction. So it's friction of the toy against the ground. It's the gears rubbing up against each other inside the toy. And now we need to account for that. Remember, we always say that heat at the beginning is 0. Even though this toy was already moving, we're going to ignore that and we always start from 0. It's the easiest way to account for energy. So I'm going to imagine stacking this EPE bar on top of this KE bar in the first frame. And I can see that the total energy comes to about here. So I want to make sure in my other graphs that my total energy will come to about this level. You can see I'm marking it on each graph. I'm just ballparking it. So I'm guessing then that the heat bar in this graph should be about this tall. I think if I stack those together, they'll reach to about this height. And in the last bar chart, all of the energy is heat. So my heat bar is this tall. All right, so that's it for these 2 examples. Please include these in your notes, and we will finish this problem set in class tomorrow.
What? What is